So most problems are worth 10 points. There were a few that were worth more than 10 points. It's always the ones that you wish weren't worth more than the other ones. But problem number 5 and problem number 13, they were worth 15 points, so it wasn't that much more. So I'm just going to hand it back. The number in the middle is your grade. The number on the left is how many you got wrong. They were curved somewhat. I curved them so that the average came out to be close to the average that I had last semester with the same students. I haven't graded yours yet because so for you guys who are online or are listening to the recording later, if you want your tests, you can come by my office. I can't guarantee I'll remember to bring them to class, but let's just go through this briefly. I'm not going to go through every detail, but so just hang on while my tablet comes up. So I'll just talk about the first two problems. The only issue there were people added the numbers together. Some people added the numbers together instead of creating two-digit numbers. They were thinking about a different problem. Number 2 was actually worth, that might have been worth less than 10 points because it was pretty easy. As far as the problem number 3, a few people forgot that there were 4 flips instead of 3 flips instead of 4 flips. So I'm going to start on number 5. So it had a special deck cards, only 10 different cards, and it says use counting principles. So the whole idea, and I think I covered this in the review, was all of the stuff we've done is ultimately comes down to the fundamental counting principle. So what you can do is you can pick 3 cards, and when you pick the first card, you have 10 options. When you pick the second card, you have 9 options. And when you pick the third card, you have 8 options. If you multiply that together, you get 720. And those are the different number of arrangements that you can have with 3 cards where order is important. Now, to get rid of the order of importance, the relationship is you can arrange n things, which in this case is cards, n factorial ways. So to remove the order of importance, which is not important in this case because it's a game of cards where you're just choosing the cards, and whether you get the first, second, or third is immaterial. So then you have to take the total of arrangements where order is important and divide by 3 factorial to remove the effect of the order of importance. And so you would take 720 divided by 6, which is 120. So the final answer was 120. So some people treated it as a permutation problem, which was definitely wrong. A few people just used the combination formula, but I said use counting principles. So some people might have gotten the right answer, but not explained it correctly. Number 6. It says use the fundamental accounting principle. So you have 2 steps. You pick a male and you pick a female. And there are 2 males, so you have 2 choices when you pick a male, and you have 4 choices when you pick a female, and so the total number is 8. That was it. Number 8, it's a problem where order is important. I most say that. So anytime you have a problem where order is important, then you should have used permutations. So you take 20 things 2 at a time, and the answer is 380. Some people got the combination problems confused with the permutation problems. Okay, number 9, that was just a straight combination problem. So you had, it says it's a committee problem, and I emphasize that a committee is a combination problem. So you take 35, you have 35 choices, you're making a 3-member committee, and that number turns out to be 6,545 once you do the calculation. Okay, number 10, you had 2 parts, and each part was a combination problem. So you would take 20 Democrats, taking 3 at a time to form a committee. You multiply by taking 30 people, the Republicans, 4 at a time, and one was 1,140, and the second one was 28,545, and you multiply them together, and you get some big number like 31,241,700. You just didn't multiply them together. Yeah, you get the problem's worth 15 or 20 points, and you get 5 points off for not multiplying them together. Yeah. Yeah. Number 11, you have 2 letters to choose from for the first call letter in the radio call thing. There are 5 vowels, and there are 21 consonants, and so the answer was 210. Number 12, it says it's a complements principle of counting. So what you do is you calculate how many arrangements you can have by tossing 6 fair coins, and each one has 2 possibilities. So that's the total number. And then to get the ones, what you're going to do is you're going to answer the question of, you're going to subtract how many have less than 2 tails. So there are 6 cases where you have 1 tail, and there's 1 case where you have no tails, which is all heads. So you get 64 minus 7, which is 57. Number 13. So it's a sample program. It's a sample problem, which is a committee problem. So what you do, again, you use the complements principle of counting. So you figure out how many ways you can arrange 8 packages, including the booby prize. So you take 8 things, 3 at a time. That gives you, let's see if somebody's got the answer here, because I didn't bring my solution with me. It was 54, 56, I think. Yeah, 56. Okay. So if you take 8 things, take 3 at a time as a sample, which is a combination problem, you get 56. And then what you do is you figure out how many ways you can arrange the remaining 7 that doesn't include the booby prize. So this includes the booby prize and all the other ones. This one doesn't include the booby prize. So you figure out how many arrangements have that in there, which is going to be 35. And so I think it is 35. Yep. And so to answer the question of how many samples do include the booby prize, you take the difference between the two. The total number with the booby prize, the total number without the booby prize, and then you have including the booby prize is one of the options, but it's not in every combination. And so you take the difference of those two numbers, you get 21. So the answer was 21. And the final problem was one of those OR questions. So if you have a single, pick a single card out of a 52 card deck, and how many ways could it be a face card or a club? So it's an or question. So that was the number of elements of A or B is equal to the number of elements satisfying condition A plus the number of elements satisfying condition B minus the number of elements that are A and B. So in our case, A is being a face card. So there are 12 face cards. The second condition is being a club. There are 13 clubs. And then you subtract the number of face cards of their clubs. There are 3 face cards that are clubs. And you get 22 as the answer. So that's the answer. Okay, so a few people, extra people came in here, so I will give you your test. Considering you didn't have you forgot to didn't watch the review, you did actually pretty good. Okay, so moving on to today's lesson. So we were talking about the probability of event A happening and event B. We could also say and event C. We actually haven't talked about it, and I haven't thought about it, but you know, if we have, let's look at these 2 cases, but we'll add an event C. So let's say there are 3 events. So events A, B, and C. So the probability of event A happening and the probability of event B happening and the probability of event C happening would be equal to the probability of event A multiplied by the probability of event B happening given that A happens times the probability of event C happening given that A and B have happened. So if you, now typically we don't ever do any problems where you have this extra level of conditional nature to it, but you have to reflect each subsequent step and how that affects the next step as far as probability is concerned. Now, more likely what happens is if we have independent events, so if they were independent, and that's what we're going to look at. If you have a multi-step process of any number of steps, all you do is multiply the probability of each step together. So you'd have the probability of event A happening times the probability of event B happening times the probability of event C happening. And you can just continue that on for however many steps you have in your process. You're upset about it. What, the test? Oh, well. So, did we do this one last time? I can't remember. About the free throws? I think we did, yeah. For some reason, I've lost the notes for the other day. We did the pet store stuff. So let's, there are a few extra card questions, and I looked at the recording for part of it. And so I made up some myself. So these are my SN problem 1. So we're asking what is the probability of the first card being a club and the second card being a club. So these are conditional probabilities. Second. So it's snowing in New York today. What is that a picture of? Oh no, that's actually Xander. Okay. Okay. So anyway, so what we do is you take in this case, we take the probability of event A happening times the probability of event B happening, given that event A happens. So first we're going to select a club. So the probability of picking a club the first time is 13 out of 52. We have 13 clubs in a full deck of cards. We have 52 total cards. If we pick a club the first time, then we only have 12 clubs left for the second choice, and we have 51 cards. So that's the product that we would end up with. We can simplify that somewhat. We would have 1/4. 13 over 52 is 1/4 because they're one suit out of 4 suits. Then you could simplify here. We've got 12 divided by 4, which is 3. So you get 3 over 51. And I think, is 51 divisible by 3? I think it is. Is it 17? Looks like it. 51 divided by 3 is 17. So the original probability looked kind of daunting as far as the calculation is concerned, but there are times when you can simplify things. Okay, the next one, first card is a king of hearts. The second card is a heart. So the probability of picking a king of hearts, that's just one card out of 52 cards. So that's my probability for the first event. The second event is a heart. Well, I've already chosen one heart here. So that means for the second choice, the second card that I choose, there are only 3 hearts left, and there are 51 cards. So that becomes 3 over 51 is 1 over 17, so we could replace that. And ultimately, you just got to multiply the denominators together. So we get 52 times 17. So it's a pretty low chance of picking a king of hearts first and a heart second. The difference, yes? Oh, well, oh, you're right. Thank you. I was thinking of something else. So yes, you're very, very correct about that. So let's correct that. So the first card is a king of hearts. That is 1 out of 52. The second card is a heart. So there are 12 hearts left out of 52. 51. Yeah, 51. Okay, so now let's see if we can simplify this thing. So we know that 3 over 50, 3 over 51 is 17, or 1/17. So that we could say that would be, if you divide that by 3, you'll get 4, and you divide that by 3, you'll get 17. And can you divide 52 by 4? Yes. What is it? How did I know I could divide 52 by 4? Because I knew I could divide 48 by 4, so I knew that. 13. Okay. So you get 4 divided. If you divide both of these by 4, you'll get 13 here and 1 there. So now you got to multiply the denominators together. So you get 221. So it's 1 over 221. Okay, so let's see if you can figure out the third one. For you guys online, give it your best shot. So the first card is a 2 of diamonds, and the second card is a 3 of diamonds. Okay. Oh, what I did was I simplified 12 divided by 51. So I divided 12 by 3 and I divided 51 by 3. I simplified it in that step. Yeah, I kind of did it in multiple steps. It was just, I remembered I used this. I knew that 3 over 51 was 1/17, and I knew that you could divide 12 by 3. So I knew that I could simplify that down using this fact. And then I said 4 divided by 52, you could divide both of these by 4, so that becomes 13. there's 13 cards in the suit. So that's how I ended up kind of do it in my head. You got it? It's a very small number. What is it?
1/2,652.
Okay. So what you did is you took the first choice. There was one card, which is the 2 of diamonds out of 52 cards, and the second one there's only 1 3 of diamonds, but there's 51 cards. So hopefully 51 times 52 is 2,652. I'll take your word for it. I trust you. Okay, so this is problem 41 through 44 in your book, if you don't want to have to copy the whole problem down. So the problem is that you can't launch the space shuttle. You can't launch it at all now because it's been mothballed. But when the space shuttle is running, you couldn't. One of the byproducts of the rockets was hydrogen chloride. So it goes in the air, and ultimately it's going to disperse, and it's going to be such a small concentration. Yes. Because it's too expensive. Yeah, it's cheaper to send them up by, I guess, the Russians. It's cheaper for the Russians to send them up. So, anyway, does anybody know? Let me ask you this question. So, when the space shuttle you did take off, you had this big main tank, and then you had these 2 side rockets. Now the main tank contained, does anybody want to know what the main tank contained? And what kind of fuel? Rocket fuel. Yeah. Do you know what kind of rocket fuel? Well, the big tank was liquid hydrogen and liquid oxygen. That's the old way of doing it. No, that would freeze our lungs. But yeah, once it vaporizes, then you could breathe it. I mean, that's what's in those. The oxygen. I'm assuming it's liquid oxygen that's in the things that people carry around for breathing. But what it is it gets vaporized and warmed up, so when it goes in your lungs, it doesn't kill you. But the other rocket boosters, they're called solid rocket boosters. So the smaller ones on the side. So those use a different kind of propellant. So let's actually check this out. A little physics or astronomy lesson. No, because they always flew out across the ocean. So theoretically, I guess somebody below them. I also think I don't know whether they used parachutes or something, but I guess even then you could get hit by one of those things. It wouldn't be too good. Okay. Yeah, they did. Instead of on land, we used to do Okay, here we go. Space shuttle. Solid rocket boosters. Okay, so here they are. They're those little things at the side, like that. And let's see what the propellant is. Well, somewhere here they got to tell you what it's made of. Okay, there it says it's propellant, but it doesn't tell me what kind of propellant. Oh, there we go, propellant. There it is. So the rocket propellant mixture in each solid rocket motor consists of ammonium percolate. Atomized aluminum powder, iron oxide, well, all small stuff. So the main thing is this ammonium percolate, which if you click on that, it's like a ammonium atom, which is NH4, plus a chlorine atom, plus 4 oxygen atoms. So you see it has chlorine in it. So if we go back to our original slide, it says it's hydrogen chloride. So hydrogen chloride is, does anybody know what, so hydrogen chloride, does anybody know what the chemical symbol for that is? Hydrogen is H, chloride, I don't know if it's HCl or HCl2 or, yeah, so the problem, so anyway, it's probably something you don't want to breathe, because if you take hydrogen chloride into your lungs, then you're going to create acid, and it's going to, the minimum is going to irritate your lungs. So that's why they don't want the weather to push the vapor from the solid rocket boosters. They don't want to push it back into a populated area. So what they do is they put the where they launch the rockets, they put on the coast, so that if it blows anywhere, it's going to, normally wind blows from west to east, so it's going to blow it out into the water where you don't have anybody living. Okay, so that's the whole idea. So what they found is that it says that it has been determined, that's by just looking at the data, that weather conditions would cause emission movement in the critical direction only 5% of the time. Critical is bad, so because it can be bad for you. Okay, so 5% of the time we have a problem. So let's write that down as a probability. So we'll say the probability of having a problem on a given day is 0.05. So we convert, yes. Yeah, well, it's not a chemistry question. I was just giving you a little insight into the chemical nature. So the probability of having a problem on a given day is 0.05. It's 5%. So now they got a couple of questions. A given launch, find the probability for an event given the following. A given launch will not result in cloud movement in the critical direction. So what does that mean? Not movement in the critical direction. So that what they're asking for is the probability of being the shuttle blowing up. It's not that high. Well, when it actually blew, the one time it blew up on takeoff or launch was, it was so high up that you wouldn't have anything. Yeah, it was. Yeah, it didn't just go. It went, and then the Challenger disaster. Yeah. And then there was the one where it was coming down, and then it burnt up. So those were the two cases. Okay, so the probability of being okay is basically the probability 1 minus the probability of not okay. Okay. So this is the complements principle. So we've gotten the not okay up here. There's a 5% chance each day it's not going to be okay. So the probability that it's going to be okay is 1 minus 0.5, 0.05, which is 0.95. So that's the answer to the first question. The probability of not being a movement in the critical direction is 0.95. Okay, the next question is, what is the probability of no cloud movement in the critical direction in 5 out of 5 launches, any 5 random days? Now, if you took this number, so this is one of these, this is probability of A times the probability of B times the probability of C, etc. And the events are independent because it's just saying during any 5 launches. So there's no reason to believe one day is going to be affected by the previous day. So there is no dependence of what happens one day on another day. So they're independent events, which means all we have to do is multiply the probabilities together. Now, if I multiplied this number together 5 times, that would give you a real small number. That would be the probability of having a problem on 5 days. But what we're looking at is the probability of not having any problems on 5 days. So that this question, you'd say the probability of being okay for 5 days is equal to the probability of okay first day times the probability of being okay for the second day times the probability of being okay for the third day times the probability of being okay for the fourth day times the probability of being okay for the 5th day. So all we have to do is multiply the probability of being okay, which is 0.95, times itself for 5 days. And that will give you the probability of being okay for 5 days without a problem. So if we do that multiplication, it's the same as 0.95 to the 5th power. And so the probability of okay for 5 days is the product of each individual day, which is 0.774. So that's saying that any random 5 days that you launch, the probability of you having no problem every one of those 5 days is 0.77, which is still pretty good. I mean, think about 5 days here that we have nice weather. Of course, we don't have nice weather 95% of the time. That's why it doesn't happen. Okay, so we use the complements principle of probability to take the given information about when you do have a problem to find out when you don't have a problem. Then we took the probability for not having a problem and used the cumulative, the and, okay first day and okay the second day and okay the third day and the fourth day and the 5th day to just multiply the probabilities together, and they're the same because they're independent events, and you get the answer. So now the next one says, what's the probability of having any 5 launches will result in at least one cloud movement in the critical direction? So this is the at least. So we've looked at that. I think it was on the test, right? Wasn't it on the test? Something. Yeah, the next to the last problem 12. If you toss 6 fair coins, in how many ways can you obtain at least 2 tails? What we did was we found the total number, and we subtracted the ones that had 1 tail or 0 tails. So we're going to do the same thing here, but we're doing it in terms of probability. The total in probability is 1. So instead of the coins, it was 64 coins. In terms of the probability, the total is 1. So to answer the next question, which is, what's the probability that in any 5 launches will result in at least one cloud movement in the critical direction? So probability of at least one problem is going to be equal to 1 minus the probability of no problems, because no problems is the opposite of at least 1. So we take 1 minus 0.774, which is 1 minus 0.774. And so you get 0.226. So that's this one. So the answer to this one was 0.774. This one was 0.226. And then finally they ask you the same question but for 10 launches. Now this one was 1 minus 0.95 to the 5th power. So to come up with this probability, we took 0.95 and multiplied it by itself 5 times. And then we got that answer. So rather than going through this long procedure again, so this is the probability of at least one problem in 5 days. So if we want the probability of at least one problem in 10 days, you take 1 minus 0.95 to the 10th power instead. So I'll plug that in my calculator. 1 minus 0.95 to the 10th power. And you get 0.401. So obviously, the more launches you have, the probability of having at least one cloud movement in the critical direction is going to increase. The probability of having no problems is going to decrease. Are you going to have anything that's difficult on the test? No, but it's just it's an example. It's a practical example of where you could use probability to answer questions like that. You know, the head of NASA is coming down and saying, "Well, what's the chances of having? My daughter's got a soccer game today. You know, what are the chances of us having a problem today? Because I don't want to miss the soccer match if it's not going to happen." And he'd say, "Well, the probability of having a problem in any of those 5 days is 0.226. They go, "Okay, that sounds good." Okay, we already talked about the birthday problem, so we don't need to do that. Okay, so we're going to move on to the next section. So this was assigned last time, so it's due next time. So we're moving right along here, having a test before we know it. Okay. So the next section is talking about binomial probability. We've done that to some extent. I mean, the previous problem that we did was a binomial question. It was, what's the chances of something happening or the chances of something not happening? We didn't ask what's the probability of happening 1 day, 2 days, 3 days. It was either one thing or the other. We talked about flipping a coin. It's either heads or it's tails. So that's just two possibilities. So here's an example of how you would take something that has multiple probabilities for each condition and making it into a binomial question. So the non-binomial question, let me just put a screen over here so you're not going to try to get too far ahead. So here's rolling a dice, 6-sided dice, and these are the probabilities for getting each number. So each number is 1 out of 6 is the probability. So this is not a binomial question. It gives you 6 probabilities instead of 2 probabilities. So how would you change this to a binomial question? Well, you would say, what's the probability of getting a 1 and the probability of not getting a 1? Yes. You could do that. Yeah, you could say, what's the probability of getting an even number or the probability of getting an odd number? So just as long as you cast the question as a yes or no or one thing or another thing, then there's a special formula that we can use to calculate the resultant probability. So if we ask the question, what's the probability of getting a 1, it would be 1/6. The probability of not getting a 1, you would either add these 5 together, which are not 1s, which would be 5/6, or you could take the probability of getting either a 1 or not a 1 And so if you take the probability of getting a 1 is 1/6, the probability of getting something is 1, so you would subtract 1/6 from 1, and that would give you the other probability. So the probability of getting a 1 is 1/6, the probability of not getting a 1 is 5/6, the probability of getting a 1 and not a 1, or actually it's not or not a 1, instead of and, because we're adding probabilities here, is or, is 100%. We're going to get something. Okay, so that's a binomial condition. So you could, like on the previous problem, clouds or no clouds, same birthday or not different birthday. So those are other examples of where they may not. The original question, you got 365 days that you could have a birthday, and that would not be binomial in nature. But if you said January 27th or not January 27th, then that would be binomial. So my daughter in Staten Island is getting snowed in today. Huh. So school's canceled, which we already knew in New York. She also, work was canceled. She didn't have to worry about it. Yeah. No. Yeah, the funny thing is in New York they have names for some of the schools. They're not usually, they're usually named after somebody. But they're also just, it's PS something. Public school 265, public school 12, or yeah. Okay, one thing that we're not going to, it sort of relates to what we're talking about here, is what is a probability distribution. If you take a higher level statistics class, you'll talk about probability distributions. We're just going to introduce what they are. So they're not binomial. Well, you could have a binomial case, but a lot of times they're not binomial. And what they do is they list the probability of all the events that are possible and show their corresponding probability values. And sometimes they're discrete, like for example, if you add the two numbers from your dice, two dice together, they have to be whole numbers. They're going to be numbers 12 or 2 through 12, 1 plus 1 through 6 plus 6, and all of those. And it can't be, you don't get 2.5 for a dice throw. So those are that would be an example of a discrete probability distribution. There are continuous probability distributions. One of the most famous is the IQ score. You know, what is the probability of me getting a certain IQ? So let's talk about both of those cases. Now, a discrete probability distribution looks like something called a histogram, which we'll talk about in the next chapter, but I'll show you what they look like. So this is a histogram. And what it is, let me put it on one page so you can see a little better. What you do is basically you have some data. And in this case, we were selling lumber in increments of 50 cents. So there's some rule that says you can't have it. I mean, of course, you probably would limit yourself to cents. But in this case, we're going to say it's $15, $15.50, $16. So it's increments of 50 cents. And then you would look at the price distribution. We'd look at lumber sold throughout the country, say, into that 1 month of 1 year, and you would find out, you know, some places it's as cheap as $15 for whatever the units are, for whatever we're buying, and it could be as much as, you know, $21. The one that's most likely to happen is the one that has the highest value. So what these are, a histogram would have the y-axis says number of occurrences. So this would be like 25 stores, and this would be 10 stores, and this would be 3 stores, and so forth. So you'd have numbers. But you can then convert those into a decimal. So what you would do is you'd add up all the number of stores that you have, say this 5,000 stores, and this might be a little over 1,000 stores, and so you take 1,000 divided by the total number, and you get a decimal number. So the question, if you went into a random store, how would you use this? You'd say, well, if I went to I had a list of stores, if I randomly picked a store, the probability of the store selling the lumber at $16.50 would be 0.24. So this would be your most likely outcome. So this is a discrete probability distribution. If I add up all these values, the corresponding y values, and I add those up, I should get 1, because it has to be they're not giving away lumber. So it's going to be one of these choices, and the sum of the probabilities adds up to 1. So that's called discrete because I have a fixed number of choices. Now this is what's called a normal distribution, which we'll talk about next chapter, but it's a mathematical formula, and so this gives you the probability if you have an average for some data and you have a certain standard deviation, then the chances of your data being in, what they're doing here is they're saying between these two values there's a 19% chance, and between these values there's a 19% chance, and between these two values there's a 15% chance. So one thing is, with a continuous probability distribution, you can't say what's the probability of being a certain number. You always have to talk about what's the probability of being between these two values, or less than this value, or greater than this value. Because theoretically, there's none at exactly any. Kind of a paradox kind of thing, because these values are actually the values that would be given would be relating to greater than or less than the value chosen. So again, it gives you an idea of what's the most likely outcome. The probability distributions do that. It's just a graphical.
Okay, your attendance question is to go into Google, search binomial distribution versus normal distribution. Go down about 4 search results, the one that's specifically for Socratic.org. And I want you to copy the 3rd paragraph from that article, which describes what the binomial distribution is, and then paste it into your discussion board.
A way of showing it. Now, with a binomial distribution, you're going to have something that looks, a probability distribution that looks like this. So for flipping a coin, it comes down to a very simple probability distribution. It's saying you get heads half of the time and you get tails half of the time. Adrienne is having a hard time staying logged on today. Must have internet problems. So let's look at another example. We're going to generate the probability distribution curve for the sum of the dice of 2. So let's generate our table. So this is, remember, this is what do they call it? Using the listing method, or using a table, sorry. So we're going to use a table to generate our sample space. So we list the 6 possibilities for the 2 dice. And then we're just going to add the 2 numbers together from each row and column. So we go from 2 to 12, as we said earlier. And each time you move this way, you increase by 1. And every time you move this way, increase by 1. Yeah, I think they were getting like 2 to 3 inches an hour of snow in New York today. It didn't last very long, but it came down like crazy. I sent my older daughter, the one who lives in in Staten Island. I sent her a text yesterday, and I said, "I put your mom on the train. She's coming up." She said she's desperate for some snow. Of course, I didn't do that, but I did check, just curious. I said, I wonder if the train was about to arrive in 20 minutes in Clifton Forge. And I thought, I wonder if there's any seats on that train. Not that I'm putting her on the train, but and they weren't cheap because they were last minute. It was like $160 you could get on, take you all the way to Newark, New Jersey. Okay, so the possibilities here are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's one case of 2, there's 2 cases of 3, there's 3 cases we have of 4, there's 5 instances of 5. 1, 2, no, am I getting lost here? 4. Yeah. There's 4 cases of 5. There's 1, 2, 3, 4, there's 5 of 6, there's 6 of 7, then you go back the other direction. 5, 4, 3, 2, 1. So this is my this would be my x-axis. This would be my y-axis of my probability distribution curve. And I'm just going to make up one here. So let's see, we go on a page. So the way you would create a probability distribution is you basically have a y-axis and you have an x-axis. And I'm just going to put in the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10. I have to make that a little bit longer. There we go, 12. So those are all my choices. And I get 1, 2, 3, 4, 5, 6. So then what I would do is I would draw little rectangles that are the height of the number of possibilities. And so each time I go here, the next one would be 1 unit higher. And the one that has the most likely chance is getting a 7. And then I can just copy these things over there. So that's what the probability distribution would look like for this particular case. Oops. So this would be, and actually the numbers here, if we're actually doing probability, you would have 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5, 36. So these are the actual probabilities. So this would be 136, this would be 236, this would be 336, 436, 536. If I did it with just the numbers, it wouldn't be a probability distribution. It would just be a histogram. So to write them as probabilities, I'm taking these numbers and dividing by the total possibilities. And if I add all these numbers together, I'll get 36, which is 1. So that agrees with what I said before. So this plus that plus that plus that. all those together will add up to be 1. Now, if I wanted to do it as a binomial situation, what I would have is I would make it into a 2 case. I'd say 7 and not 7. So the probability of me getting not a 7 or getting a 7 is 6 out of 36. And my probability of getting not a 7 added together would be the remainder. So this height would be 6 divided by 36, and this height would be 30 divided by 36. So when I add these two together, I still get 1. This one's a binomial question. This is not a binomial question. Shooting free throws. That's a binomial situation. You don't have to make it a binomial situation. It's going to be, you're going to either make the free throw, which is 0.8 probability, or miss the free throw, which is 0.2. So this is the formula. If you have a binomial situation, then you can calculate the probability of success of so many trials out of so many, so the number of successes per total number of trials, you can figure out what that number is. So, you know, if I'm using, if I'm flipping a coin, I want to know what the probability, if I flip a coin 5 times, what's the probability of me getting exactly 3 heads? What's the probability of me getting exactly 2 heads or 1 head? How do I figure that out without having to go through a complicated analysis every time? So what you do is use this binomial probability formula. And what it says is the probability of X number of successes is equal to, we use the combination formula, the combination of N things, which is the number of trials, taken the number of successes. So if I had three heads out of 5 flips, N would be 5 and X would be 3. And then you take P. P is the probability of success. So flipping a coin would be 0.5 success, 0.5 failure. Q is the probability of failure. You raised P to the X power, which is the number of successes, and you raise Q to the number of failures, which is the total number of trials minus the number of successes, gives you the number of failures. So this plus that, you can see X plus X minus 1 equals, X plus N minus X is just equal to N. These two numbers always add together to give you that number, and these two numbers are always the same. So that's how it works. So we'll do some examples of how you can figure this out. Use this formula, and you'll use this on the test for sure. So let's use a coin question first. So what is the probability of getting exactly 3 heads when flipping 5 coins, 5 fair coins? Question mark. So here's the formula. We just have to figure out what, based on the problem statement, what is each thing, what are the values for the different variables. So N is the number of repeated trials. What is a trial in this case? It's flipping a coin. So N is 5. What's the probability of success of any given trial? Well, the probability of success, which is getting ahead, is 0.5. The probability of failure is 1 minus the probability of success, which is 0.5 in this case. So it's 0.5 for getting success and 0.5 for getting a failure. X is the number of successes. Well, since I defined getting ahead as a success, the number is X is 3. So to find the probability of getting 3 heads out of 5 flips, you take 5 things taken 3 at a time. You multiply by 0.5 raised to the x power, which is the third power, and you multiply by 0.5 raised to the 5 minus 3 power. So now we just have to do the calculation here. So the first thing I'm going to do is I'm going to do the math in the exponent. So I get that. Okay. 5 things taken 3 at a time. That was n factorial over r factorial times n minus r factorial. So that's 5 factorial divided by 3 factorial times 5 minus 3 factorial, which is, we divide by 3 factorial and 2 factorial, and then we convert 5 factorial into 5 times 4 times 3 factorial, divide by 3 factorial and 2 factorial, cancel out the factorials. You get 5 times 4 divided by 2 times 1, which is 10. So that's the number, 5 things taken 3 at a time. So our final answer, the probability of getting 3 heads, exactly 3 heads, is going to be 10 times 0.5 cubed times 0.5 squared, which is 10 times 0.5 to the 5th power. So you add the exponents when you have the same base. So we take 10 times 0.5 cubed to the 5th power, 10 times 0.5 to the 5th power, and you get 0.3125, which is 3/8, I think. No, it's not. What is it? 5/16 maybe? 5/16. So that's the probability of getting 3 heads exactly. And it's a binomial situation. It's not a binomial situation. The actual trial is a binomial trial. I mean, ultimately we have the probability of getting 0 heads, 1 head, 2 heads, 3 heads, 4 heads, or 5 heads. But each calculation involves a binary choice in the original question. So you can do the same. You could do the same thing for 0 heads, 1 head, 2 heads, 3 heads. We actually, if you remember, back when we talked about Pascal's triangle, we were saying if you wanted to do these, in this case, you'll notice it doesn't matter what the exponents are here. They're always going to add up to be 5. So this thing always stays the same. And if you take 0.5 to the 5th power, let's take 0.5 to the 5th power, you get, well, actually, let's do it this way. 0.5 to the 5th power is 1/2 to the 5th power, because that's the decimal equivalent of that fraction. So that's 1 to the 5th power divided by 2 to the 5th power. 1 to the 5th power is 1. 2 to the 5th power is 32. So for all these cases, whether you have 0 heads, so we have 0 heads, 1 head, 2 heads, 3 heads, and I could calculate these for all of them using this method, but I'm going to just do a little shorter to show you how you would get this 5 heads. So those are all the different choices, possibilities. And we just did 3 heads, which was, it was 10 over, ultimately it was 10 over 32, which then simplified to 5 divided by 16. And back when we did this in the previous chapter, we said, you know, you could use 5 things taken 0 at a time, and 5 things taken 1 at a time, 5 things taken 2 at a time, 5 things taken 3 at a time, and so forth, to find out how many occurrences there were. And the numbers, the corresponding numbers were 1, 5, 10, 10, 5, and 1. So it turns out the probability calculation is these are the numbers in the numerator, and these 32 is always in the denominator. So when you have two heads, you're going to have 10 over 32. Here you're going to have 5 over 32. Here you're going to have 1 over 32. And you have 5 over 32 and 1 over 32. And if you add all this together, you get 1. So you have, we're just using something we learned in the previous section, but if you didn't know that, you could still just use the formula to be able to do that. Now, when you have probabilities that are different than 0.5, it becomes more complicated. So we can only do that. We can only do that simplification or easy explanation if it was flipping a coin. If it wasn't a flipping a coin, you couldn't say that is true, because you might have 0.8 cubed and 0.2 squared, and it doesn't come together quite the same way. Okay, so that's one example of binomial probability. So here's one. This is in the book. Assuming baby boys and baby girls are equally likely, find the probability that a family with 3 children will have exactly 2 boys. So it's a binomial situation. You have a boy or you have a girl. The trial is a binomial situation. Because it's equally likely, just like flipping a coin, the probability is 0.5 for having a boy and 0.5 for not having a boy. In our case, because we're asked the question, what's the probability of having exactly 2 boys, we define having a boy as a success, and we've defined failure as having a girl. Yeah, well, we're just not trying to carry here. We're just, if the question asked us exactly 2 girls, then success would be having a girl. It's just the way that the question's asked. So basically, again, what we have to do is figure out, to be able to calculate this question, probability question, is to figure out what is n, which is the number of trials. We need to know x, which is the number of successes. We need to know the probability of success, and we need to know the probability of failure. Once we know those 4 things, then we just plug it in the formula. So we look at this and we say, okay, what do we have? 3 children. So the number of trials is having a child, having a baby. The number of successes is 2, because we want to know what's the chances of having exactly 2 boys. Because they're equally likely, again, the probability of success and failure are the same thing. So to answer the question, probability of exactly 2 boys, it's going to be c to the, taking n things, x at a time, probability of success raised to the x power, and the probability of, that's an x, to the n minus x power. So now we just plug it in. So we get 3 things taken 2 at a time times 0.5 to the 2nd power times 0.5 to the 3 minus 2 power. 3 things taken 2 at a time times 0.5 squared times 0.5 to the 1st power. 3 things taken 2 at a time is just 3. And then you have 0.5 cubed. And if you plug that into your calculator, 0.5 to the 3rd power times 3 is 0.375, which is 3/8. So the probability of having 2 boys is 3/8. The probability of having 1 boy is 3/8. The probability of having no boys is 1/8. The probability of having all boys is 1/8 as well. Yep. I don't think so. You just have to do the calculations. Okay, so all we've looked at so far are these 0.5 probability cases. Let's skip those for a second. So here's the last question. We may not get it finished today, but we'll come back and do that ones. So the game is tied, and there's 1 second left on the clock. The Mountaineers have fouled the Cougars' best free throw shooter while he was attempting a 3-point shot. What is the probability that the Cougars will win the game if their shooter has a free throw percentage during the season of 76%? So to win the game, he's going to have to make all 3 free throws. So the number of trials in this case, now, so we're taking this and we're converting it into the language of binomial probability. The number of trials in is 3 shots. The number of successes has to be 3 to win, 3 successes. The probability of success is 0.76, and the probability of failure is 1 minus 0.76, which is 0.24. So we've got everything we need. So the probability of 3 out of 3, which is winning the game, is going to be equal to 3 things, taken 3 at a time, times 0.76 raised to the 3rd power times 0.24 raised to the 3 minus 3 power. When these numbers are the same, the answer is always 1. If this is 0, it's also 1. So these are the outside of Pascal's triangle. So you get 0.76 cubed, 0.24 to the 0 power. Anything to the 0 power is 1. So you get 0.76 cubed times 1. And the final answer is 0.44. So about half the time they'll win the game, and half the time they'll lose the game. Of course, obviously, the better free throw shooter he has, the higher the probability they'll win. If you get somebody who's really bad at free throw shooting, like Shaquille O'Neal, let's just stick his numbers in quickly. So the Shaquille O'Neal, let's say he shoots 40%. I don't know if that's what he shot or not. But you'd have 3 things taken 0 at a time. The probability of success would be 0.6. The probability of failure would be 0.4. This would be to the 0 power. This would be the 3rd power. So you'd have 1 times 0.4 to the 3rd power, which is 0.064, or 6.4% of the time, which is pretty low. So that's why you would yeah, in some way. Well, maybe not. I mean, it just shows you that for somebody who's even a 40% free throw shooter, for them to get 3 shots in a row doesn't happen very often. It's a miracle almost. Yeah, I don't know much about baseball. Okay, let me assign the homework from this section. So we'll do that, and then we'll finish this section up next time. So there you go. That's due next Thursday. So since we'll probably finish this, I'm just trying to think about the next test. We'll probably finish all the material by next week. So what I'll probably do is, it'll be the following week, but I won't make it Tuesday, I'll make it Thursday. So the next test is most likely going to be, let's see what date. So we'll finish next week, so it'll probably be the 23rd of February. Maybe the 21st, but probably not. I always like to give an extra day just in case anybody needs some help. Let's see, did anybody not get a test? Did you